In this short video lesson on sections 10.3 and 10.4, we'll be looking at kinetic and potential energy and discussing the following. You will need to be able to understand kinetic energy, its equation, and the components. You need to be able to understand both gravitational and elastic potential energy and the equations for them. You'll need to understand how Hooke's law applies to elastic potential energy. And finally, you will be able to explain the importance of reference levels for gravitational potential energy and equilibrium positions for elastic potential energy. We will begin with kinetic energy, which is also known as energy of motion. And there are two types of kinetic energies that are covered in the book. The first one is translational, which is motion along a path. And the equation for translational kinetic energy is K equals 1/2 mass times the square of the velocity. So make sure you understand how those variables go together. The kinetic energy is directly related to the mass, and it's directly related to the square of the velocity. So if the mass increases, the kinetic energy increases likewise. But if the velocity increases, well, the kinetic energy increases by the squared amount. The second type of kinetic energy is rotational kinetic energy, and that's motion around an axis, something turning in a circle. And the kinetic energy for that is 1/2 times the moment of inertia times the angular velocity squared. Now you'll probably be glad to know we will not be spending much time with rotational kinetic energy in this chapter. As a quick reminder, please remember that when we are talking about all of the energies in these problems, we're often talking about the change in energies, whether it's kinetic, potential, thermal, whatever it might be. So please remember that the change in energies is the final energy minus the initial energy. Also, all of the energies that we will be studying have joules as their unit. There are two types of potential energies that we will study, and we'll begin by looking at gravitational potential energy. This is the energy that could be released if an object were to fall from a certain height. It could also be thought of as the energy required to bring an object up to a certain height. So whether something is falling from a height or you're lifting it to a height, there's some sort of potential energy involved. Gravitational potential energy depends upon three things. First, the mass of the object. An object that is more massive requires more energy to lift and releases more energy when it falls. Second is the gravity of the location. Earth has a pretty standard gravity all around, but if we were to go to a different planet, the gravity might have an effect on the potential energy. Finally is the height to which it is raised. Objects raised to a greater height will release more energy, obviously, and it takes more energy to lift something to a greater height. These three things come together to give us the equation for gravitational potential energy, and that is U sub g equals mass times gravity times the displacement in the y direction. Gravity is a conservative force, which means that basically whatever you put into it, you can get back out. You can lift something up to a height, and then you can let it fall back down to its original height. Because of this, there are two important characteristics that we can use when addressing potential energy. First, we can set the reference level, or the zero level of height, at whatever point we want to. So in this picture, the zero level, the reference level, is set on the ground, and the man goes up to 200 meters. If we had wanted to, we could have set the zero level up at the top, and he began at negative 200 meters. It's pretty customary, though, to set the reference level at the bottom, on the ground. The second thing is that it doesn't matter which path you take to go from the reference level to your final height. You will be looking at the change in potential energy from the beginning to the end. And it doesn't matter which of those two paths he took, it's still the same change in gravitational potential energy. Before we understand elastic potential energy, we need to spend a little time understanding how springs work. Now here we have a spring up at the top, which is at rest. In other words, it's not being stretched or compressed. It is at its equilibrium length. So at this point, the displacement is 0. In the middle figure, the spring has been compressed, and it has been compressed a displacement of delta x. Now obviously the spring wants to push back, but it's being held for right now. In the bottom picture, we have a spring being stretched, and it's also stretched a distance of delta x. And that spring obviously wants to go back to the equilibrium position. So in each of the bottom two cases, when we apply a force to the spring applies a force backwards in the opposite direction. This force is explained by Hooke's law, which states that the spring force is equal to the negative spring constant times the displacement. Now let's look at the three parts of this very quickly. Delta x is the displacement, in other words, how far you stretch or compress the spring. K is something called the spring constant, and it's different for different springs. Obviously, it's much harder to compress a very tight spring than it is a very loose spring. Finally, the negative sign just means that the spring is always trying to act in the direction opposite of the displacement. If you push the spring in, it tries to push back. If you pull the spring out, it tries to pull back. We can now use this understanding of the spring force to better understand elastic potential energy. Without going through all of the algebra showing you how this is derived, instead I will just give you the formula for elastic potential energy, and it is equal to 1/2 times the spring constant times the displacement squared. So here you have a summary of the three types of energies that we have discussed in this lesson. There's kinetic energy, energy of motion, given by 1/2 mv squared. Gravitational potential energy, or energy of position, given by mass times gravity times the displacement. And finally, elastic potential energy, which is given by 1/2 kx squared, where k is the spring constant. Now please don't forget all of these energies are measured in joules, and make sure you understand how the zero reference point in gravitational potential energy is applied, and how the equilibrium position when a spring is at rest determines the displacement for elastic potential energy. We'll be using these equations to solve problems in class tomorrow.